In section 6, we're going to look at probably the best real-world application when it comes to lines. We're going to fit lines to some data we have and also look at some terms that help us describe relationships between data. So these will be some skills that you would actually use in science or studying social science. When you see reports on the news, some terms that you might see there, or some connections that you will maybe want to be able to make between different variables or values in studies that you might see. So I would hope that you know what a scatter plot is. A scatter plot is just a graph of some set of data points. Maybe you collected data about people's height and weight, or age, and how many hours they sleep. And you plot those on an XY coordinate plane, and the result is a scatter plot. A scatter plot can be helpful because it helps see connections or relationships between the data. And that's something that we call correlation. So if you look at this word correlation, two things correlate, right? We see the word relation in there. So correlation describes the relationship of variables. Okay. There's 3 different types of correlation. We could have a positive correlation, a negative correlation, or no correlation. So this first graph down here is an example of a positive correlation, because as one of these variables is increasing, so is the other. So it'd be helpful if we could sit here and have discussion. If you're in class, then we will, about some things that might have positive correlations. So for example, if we were to plot height and weight, you would probably expect to see a little bit of a positive correlation. Right? The taller somebody is, the more they probably weigh. Would that be a very tight set of data? Not necessarily, because you can have some tall people who are very skinny, some shorter people who are a little bit stockier. And so there's some variety, but you would probably see a positive trend in that data. As one of those increases, so does the other. We could also have a negative correlation, which shows a trend, but in this case, as one of them is increasing, the other variable is decreasing. Okay. Something that could have a negative correlation might be hours of studying versus how long it takes to complete a test, right? You would think that the more hours you studied, it would take you less time to complete a test. That's not always the case. You'd hope that wouldn't go the other way, right? You wouldn't hope it would take you longer to finish a test if you studied more. But that might be something that has a negative correlation. Or if you have a girlfriend, the more time that you spend with your girlfriend, the less money you're going to have in your wallet, right? That's a negative correlation there. Okay. And then lastly, things might have no correlation. We could collect data and have it have absolutely no relationship. I could collect your age and ask your favorite number, and there's probably no correlation between somebody's age and favorite number. I don't know if you even have a favorite number, if that's a thing. I don't know that I have a favorite number, right? Or your height and your jersey number. There's probably no correlation between those two things. It's kind of random, but this shows that there's no real connection. One important thing to remember and consider is correlation is not necessarily the same as causation. And that's important to remember as you guys begin to be more involved in the world and you see the news and studies and headlines. Just because two things might be correlated does not mean that one of these causes the other, right? So you'll see on media people trying to promote an agenda and say, well, as this happens, so does this. But that doesn't mean that one is causing the other. There might be some third condition that's causing both of them, right? So be a good citizen when it comes to interpreting those things, and don't jump to conclusions. Just because two things might be correlated does not mean that one of them is causing the other to happen. We can have different strengths of correlation. There might be some data that we plot, and maybe those points are in almost a perfectly straight line. As one goes up, so does the other. Maybe that data is a little bit more spread out. We can see a trend, but it's not like a clear line, but we still see some trend. Or maybe, again, we plot something and there's absolutely no relationship. We can find a value. We're not going to do this. We could find some data, plug it into like Excel, and use a formula there, run some analysis, and it would spit out a value for us that describes the strength of a relationship between two variables, and that's called the correlation coefficient. And this correlation coefficient can range from -1 to 1. Okay. If the coefficient is positive, that means we have a positive correlation. If that coefficient is 0, we have no correlation. And if it's negative, we have a negative correlation. If we end up with a correlation coefficient of 1, that means that our data is exactly on a straight line. So the chances of that happening are pretty slim if we're actually collecting real-world data. But that means we would have an actual straight line. So a correlation coefficient of like 8 or 9, right, would be a very strong positive correlation. So something like this might have a correlation of 0.8 or 0.9. It's a very tight positive correlation, right? This next one, we still see a positive correlation, but it's not as tight of a relationship. The data is a little bit more spread out. There's a little bit more variation, but we still see a positive trend. So this one might have a correlation coefficient of, I don't know, 0.4 or 0.5, right? This last one, there's no real trend with that data, so we would expect this to come back with a correlation coefficient of 0. Okay, so on the assignment, I think you're given some of these, or maybe you're asked to draw a graph with certain correlation coefficients. If I wanted a negative one, so if I wanted a correlation coefficient of negative 0.9, we would see a plot something like this, where there's a negative trend of very tightly grouped data. So once we do have data, sometimes it's helpful to create what's called a best fitting line that kind of describes the data, and it would also allow us to predict future or other values, right? If we don't have, so like let's say here, we don't have a value for when x is 7, so we could make what's called a best fitting line and then use that line to make a prediction for what the value would be if x was 7, or even extend it on further to somewhere we don't have data for, and make a prediction when x is 15 or 20. Okay, so first of all, the first step to make a best fitting line would to be draw the scatter plot, and I think I forgot to put the table of values here, but everything's on a nice even point so we can see what all the values are. But you're given some data, you draw a scatter plot, and then what we need to do is draw a line that seems to fit the data well. So it should split the points above and below. It should kind of go right through the middle, right? Something like this would be a poor choice for our line because it's all above, right? Or something down here that's below, another poor choice. And then here's maybe a loophole. That cuts the data in half, or at least close. But it obviously doesn't follow the trend of the data, so that's another poor choice for our best fit line. So what we'd want to do is draw a line through our data, and you probably want to try to hit at least 2 of the points. So I think I maybe kind of hit these, or could have if I had a ruler, right? But let's say I hit those 2 points. It's helpful if you use actual points, or if you do hit like an exact point. That's not one of them, but say like we went through this here, it looks like we hit 5, 5, right? We could use that. But now we have 2 points. What do I have? 2, 3. And over there to the right, I have 9, 8. What I could do now is what we had done last section and write the equation of the line that goes through those points. Right? Find the slope of the line, and then finish finding the y-intercept to get the equation y equals mx plus b. And then that would give me the equation for my best fit line. So then if I did want to know something about when x is 15, I could plug in 15 for x in that equation and have an estimate of what the y value might be for that. So like let's say that this was time, right? And we have a population that's growing, and right now it's only this year. So we only have data up to there. We can't collect data further on, but this would maybe allow us to predict what the population might be down the road based on the past trends.